Good afternoon and welcome to the webinar. Today's webinar is called Extending STK Mission Models with Detailed ANSYS Engineering Simulation to Track Hypersonic Vehicles from Space. I'm Josh. I'm going to be doing some of the behind-the-scenes stuff from this webinar before I pass it over to the presenters. If you have any questions, we want this to be interactive. So over in the GoToWebinar, there is a questions panel. Please type any of your questions in there, and at the end of the presentation, after all the speakers go, I will read them to them, and they will do our best to answer them in the allotted time. Some of the questions may be something we'll have to follow up with, but we will get to all of them. Maybe not live during the webinar, but at some point we'll be answering anything that you put in there. And like I said, we have a bunch of presenters from several different companies all around the country today, and I'm going to not introduce them all right now. They will be introduced at their time of presenting, but I'm going to start off with Jeff Baxter, who heads up the engineers here at AGI. And Jeff, over to you to kick off this presentation.
All right, thank you, Josh. And thanks to everyone for joining us here today. A special thanks to everyone that has attended multiple in this series. We're in the last series finale here, the fourth webinar in digital mission engineering. I want to thank this webinar's co-presenters from ANSYS, Ming, Sean, and Valerio. And also special thanks to Joshua Edwards from Phoenix Integration, who is joining us for our third installation here today. And so this is really the grand finale of this digital mission engineering series. In part one, we introduced what digital mission engineering is and why it's important. Part two began to show how to apply digital mission engineering, starting with early concept development and trade space exploration. In part three, we showed how to integrate descriptive models with physics-based mission models. And then today, I'm really excited because we're going to really focus on the detailed engineering design phase and show how to extend the mission model with pervasive engineering simulation. We'll show several demonstrations with our partners throughout that go into detail on a variety of areas, including thermal, communications, and hypersonics, and how that all fits within the digital mission engineering ecosystem. We have a lot of really great content to cover, a lot of great presenters, and not a lot of time, so let's go ahead and get started. As we discussed in previous webinars, digital mission engineering is the use of computer-based modeling, simulation, and analysis to evaluate mission objectives. And really the focus is all about the mission. When programs are created, they're meant to meet a need, a gap, a requirement that will help achieve the desired mission objective. And as a commercial software provider working with hundreds of organizations throughout aerospace and defense, we get a pretty broad perspective of the industry. And one of the trends we're seeing, especially right now, is that systems are getting more complex at the same time that development cycles are getting faster and less forgiving. And you see the arrow representing the complexity increasing, the delivery time decreasing, which is putting a lot of pressure on the industry to improve our engineering practice and deliver better systems faster. And traditional methods of developing tools cannot really keep up with the pace here. And so in A&D, traditional document-based requirements mean lots of time and effort go into building custom, incompatible, and unconnected models and tools at each level of component, subsystem, or system level. And so digital mission engineering addresses these by moving toward a model-based engineering approach where the model becomes the ultimate source of truth. Model can persist throughout the life cycle of the system. And as the mission changes or requirements change and evolve, the model can also change and evolve. So what we see today across the industry is, as I mentioned, a lot of isolated models, reinvention of stovepipe tools, and no common thread across the program lifecycle. So if we look at this in this diagram, starting at the concept development phase of a program, there are typically some basic mission models that may loosely depend on physics to help understand the concept of the system. And as the program matures, a new mission model is typically created to handle more detailed physics models. And typically there will be multiple individual tools that all do a certain type of function for their specific special area. And then these models are then used to define the requirements thread, which is then used throughout design and implementation, and then ultimately out onto the testing phase. And this design and implementation is typically the least and the furthest separated from the mission model and the mission level. And once the system is finished, new mission models are then created for that system to evaluate how it's performing against that mission need. Typically, a new mission model is used for training, operations, and sustainment. And the cycle then starts again as the initial system is deployed and future improvements are made. And so as you can see, this leads to a lot of isolated tools, reinventing the wheel, and it makes it really hard to tie everything together. And if this is just looking at a single program, so as new programs come online, even similar programs, the process usually starts over from scratch. And so the vision of digital mission engineering is to connect all of the component, subsystem, and system models to the mission model that is rooted in a multi-domain physics environment. Furthermore, these models need to be pulled in all and integrated as early as possible in the process and then persist throughout the life cycle. So an important concept here is this concept of a digital thread, which represents how each of these models are individual strands that are tied together like a thread, so that when you change individual parts of one model, it pulls through the rest of the models as well. And in order to achieve this vision, it really requires an ecosystem of commercial tools that all integrate together from day one. So without that, it makes it really difficult to identify critical issues early on in the process, which can limit the overall delivered effectiveness. So in previous webinars, we started building a representative demonstration that highlights the early phases of this vision applied to satellite constellation design. We quickly built a mission model of a constellation covering select ground locations, integrated that with a cost model, ran some cost versus performance architecture level trade studies, and then linked those mission models to a descriptive model in SysML. And today's webinar, we're going to build off this demonstration by using the orbit information calculated from that satellite constellation design. And we're really going to focus on an individual spacecraft and dig into a lot of the technical details at the subsystem and component level. And one of the key enablers of this is our recent partnership with ANSYS. And the reason we're so excited about this new partnership is that we're really providing a full digital mission engineering stack that connects components, subsystems, systems, and system of systems to the mission model. So when you think about the engineering enterprise, mission level problems are broken down into executable pieces: component development, subsystem integration, and system integrations. In use, these complex systems come together in a system of systems architecture, must operate in a coordinated way across multiple domains and achieve the desired mission outcomes. So really that's what the mission and what we're talking about here. And you can do this at multiple levels. You can do it at the local level, at the regional level, and all the way up at the global level. So really that's what this partnership enables. It connects all of these digital models from the components to the system of system architectures to successfully evaluate mission objectives. And so an important component in digital engineering is also this concept of the digital twin, which is, there's several definitions out there in the industry, actually multiple industries. And this is a simple definition, which is an adaptation from the DoD definition, which is simply an integrated multi-physics simulation of a physical system that pairs the virtual world to the physical world. And there's an article in Forbes magazine that described this process of the pairing of the virtual and physical worlds that allows analysis of data and monitoring of systems to head off problems before they occur, prevent downtime, develop new opportunities, and even plan for the future by using simulations. And so the whole idea here is that lessons are learned and opportunities are uncovered within virtual environment that can be applied to the physical world, and as they described, ultimately transforming your business. So what we want to show here is, now that we're talked about the concepts of digital mission engineering, including the digital thread and the digital twin, we want to show all these in action. And so we're going to jump into some demonstrations now that start going down that path. And I'd like to start off, first of all, by thanking our friends at Astro Digital and ASI who provided the CAD model and digital spacecraft simulation model for this Corvus BC spacecraft, 6U CubeSat, which is actually running the same flight software on orbit that we used in this simulation with STK SOLIS. So we'll be using this Corvus BC spacecraft as the example satellite we'll be using as our notional satellite constellation. And we're going to really dig into a lot of detail on this spacecraft. And on the left, you can see the physical layout of the system. On the right, you can see some of the images of the engineering and mission simulations we've run. So the CubeSat has several subsystems, and today we're really going to be focusing on the attitude control system, multispectral imager, and Ka band radio. And we've modeled each of these subsystems in STK and ANSYS, and we'll evaluate their ability to meet mission requirements across a couple different use cases. So real quick, this is the inputs that we used for modeling the attitude control system. There are 3 reaction wheels and some magnetic torquers that we've defined. And we set up what's called a target plan based on a deck of targets, both ground target locations as well as scans, and then downlinking the data to a ground station. And this is a snapshot of what the mission simulation looks like. You can see the spacecraft slewing to its particular target, the sensor field of view collecting that target. And the image on the upper right shows the reaction wheel speed in order to slew the spacecraft to collect these targets. And in the lower right-hand corner, we see the thermal loading from the sun and the Earth albedo and Earth planet's IR. The yellow vector represents the direction of the sun vector in this case. And so this is the interface that we can expose to report all of those elements out from the mission model. There are thousands and thousands of these parameters. So in this case, we chose the flux from albedo, the planet's IR, and the sun as the thermal loads that we want to then run into ANSYS for the dynamic thermal loading on the spacecraft and all of the components itself. So here's a quick video that highlights this as a typical imaging pass. Our satellite is required to collect these ground targets and scans and then downlink that data to the ground station. And you can see the relative geometry. Each of the faces is exposing different areas to the sun, to the Earth albedo and the IR. Throughout the entire pass. So you can see here that the mission environment is playing a huge role in our thermal analysis, starting with the orbital altitude and inclination from the constellation from previous webinars. And now we've used SOLIS to model the attitude control system to point the spacecraft at the targets. And then we're going to pass this over to ANSYS for higher fidelity thermal analysis. So with that, I'll turn things over to Ming from ANSYS.
Hi everyone. So this is Ming Xu from ANSYS. I'm application engineer with ANSYS Mechanical. In the next few slides, I will present the demo for transient thermal analysis of CubeSat using ANSYS Mechanical, coupled with the AGI STK tool. Next slide, please. Thanks. The thermal analysis of the CubeSat is performed in ANSYS Mechanical transient thermal solver. When the CubeSat is in the orbit, it's constantly exposed to solar heat flux and the Earth's albedo, and will also radiate heat into the space. ANSYS Mechanical will take the heat flux time history of the CubeSat, calculated by AGI STK, and calculate the thermal performance within the satellite. I also want to mention that ANSYS Workbench is a multi-physics platform that can integrate different solvers together. For example, using the coupling analysis of ANSYS high-frequency electromagnetic field solver HFSS and transient thermal solver in ANSYS Mechanical, ANSYS customers can simulate thermal buildups in external antennas and internal electronics to check if antennas are subjected to a potential risk of loss of efficiency and drifting of desired tune frequency. Then, considering the thermal strain calculated by the thermal solver, we can perform structural analysis, model analysis for natural frequency, and random vibration analysis, and so on. In the transient thermal analysis, each phase of the CubeSat will have different time history of heat flux. ANSYS Mechanical will apply the heat flux as boundary conditions and also add the radiations of the external surfaces and the internal components of the satellite. The solver will calculate the temperature distributions versus time and the heat flux within the satellite. Calculated values can then be used in structural analysis, considering as the thermal effect. This slide shows the temperature distribution within the satellite changing with time. As you can see, at different time point, the temperature will be changed. This slide shows the heat flux in the satellite during the simulated period of time. This is also actually the heat flux at different areas of the satellite will changing with time. So this will conclude my demo for the transient thermal analysis of CubeSat in ANSYS with a high fidelity thermal solution calculated by ANSYS Mechanical. The model is ready for analysis of other physics. Next speaker up is my colleague, Sean Carpenter from ANSYS. He will talk about the utilization of ANSYS high-frequency electronic tools on the CubeSat.
Great, thank you very much, Ming. And hello, everyone. My name is Sean Carpenter, and I'm a product manager for high-frequency electromagnetic analysis with ANSYS. As Jeff has already indicated, this technical partnership between AGI and ANSYS has the potential to more effectively connect your systems and mission engineering groups to your subsystems and components engineering teams by bringing high-fidelity physics models into the mission simulation domain. Now, next slide. I'll be talking about how this might apply to the RF telemetry system development and its validation in our digital mission engineering simulation for our candidate CubeSat. Now we have here, again, illustrated the CubeSat components and the subsystems. Next. And we're going to focus in this section of the presentation on the Ka band radio system. And you can see the specifications for the radio there on the right-hand side. Now, in particular, we're going to be looking at the antenna system. And this system is operating at a Ka band, so it's in the neighborhood of 30 gigahertz. And you'll see here in particular that it has a main beam focus of about 10.2 degrees. That's the half power beam width. And this whole system fits into a very nice compact size. It's inside of a 1U volume. Next slide, please. Now the land map or a CubeSat has 3 optical sensors, which you can see is the white openings that are kind of on the upper side of the body. And then the Ka band aperture is shown with a more yellowish opening that you can see there on the body of the satellite. Now for this demonstration, we'll be leveraging a high fidelity, full physics electromagnetic analysis by the ANSYS High Frequency Structure Solver, or HFSS, which is a high frequency field solver used to assess 2 performance measures of interest for this study. First of all, we'll be looking at how the antenna performs in isolation. This is typically how we would normally measure a prototype. We'd put it in an anechoic chamber on a test table all by itself, and we'd measure its radiation characteristics. But second, and perhaps most important for integrators, is how the antenna performs when it's installed on the CubeSat. There will be electromagnetic coupling between the aperture and the platform body, the solar panels, and the other structures, which may serve to alter the antenna aperture performance. But the question is, how much? Now, we'll use the installed performance data from this simulation in the overall satellite mission simulation so that this realistic antenna radiation pattern is used then in the overall telemetry link budget model employed in the STK software as the mission evolves. Now, our EM analysis will provide installed radiation patterns for both the copole radiation, that's right-hand circular polarization as defined from the transmitter point of view, and the cross polarization patterns, or the left-hand circular polarization. Next slide, please. And next. Now, the process for modeling the antenna is pretty straightforward. First, we were provided a step model, a CAD model containing the structure, the 3D structure, and the major components of the CubeSat. Now, this was imported into the analysis suite to see the CubeSat structure and to get at the various internal components. Next. Then we isolated the transmitter component, and we captured the model from the circular waveguide opening upward into the antenna. Now, we have the freedom to apply excitations of any polarization we wish, and a right-hand circular polarization was selected to match the mode of operation for this device. The ortho mode transducer was dropped out since the internal detail of the polarizer and the connection to the power amplifier and so forth were not included in the CAD model, but it's the antenna here from its feed point that's of particular interest for this study. Now, we were not provided with an explicit description of the materials, but we took an educated guess that the lens on the aperture opening, which is used both to focus the EM energy and to protect the interior of the horn and waveguides, was a Rexolite material. So our solver has a fairly extensive database for the dielectric and conductive properties of materials, so we applied the material properties for Rexolite from that database. Now the lens also has, and you can see the cross section there in that kind of grayish area, it has some shape approximation that appear to be sort of facet-like that are probably an artifact of the simplification of the CAD model for model export. And this is likely to affect somewhat the model's prediction of beam focus and probably side lobe level control. Next. Then finally, we let the HFSS solver do the work. Now, our solver employs automatic adaptive meshing in order to find the best balance between convergence of results and the minimization of computer and time resources required. Engineers who use this tool do not need to become experts in creating good solution meshes. The solver does that work. The solver also provides post-processing to display and to export quantities like the electromagnetic fields, the far field radiation pattern characteristics, and the feed point characteristics to evaluate the power match to the power amplifier. Next slide. The results for the simulation match the measured beam width of 10.2 degrees nearly exactly. Now on the left you can see from a paper published by the authors or the designers in an AIA conference paper on the left-hand side. So the copole of the right-hand circular pole is on the left, the left-hand circular pole or cross pole on the bottom, and then the HFSS simulation results are in the graphs in the middle of the slide. Now the side lobe levels and the transitions on the side of the main beam are a little bit different from what the designers reported in the conference paper, but it's probably due to the lens model facetization. And I do believe a high fidelity NURBS model of the lens will likely pull those results in even more closely. Finally, on the right, you can see a time animation of the fields in this device at 30 gigahertz, and this shows the march of the fields down the waveguide, out the flared horn, and through the lens. And from this display, you can kind of get a sense for how the fields are bending in the lens to present a nearly flat wavefront as they exit the volume. Next slide. And next. The next step in our modeling process is to integrate our antenna model back into the CubeSat body so that we can assess the impact of electromagnetic coupling to the platform. And here you can see our EM fields from the model inside of the horn and exiting to a small, you can kind of see a box-like near field boundary just outside of and surrounding the RF aperture. This region is solved using our finite element simulation. So that's what's going on inside of that simulation volume. Next, please. But the region outside of this box is solved using a different electromagnetic analysis technique called shooting and bouncing rays. The full CubeSat body is really fairly large for a finite element volume meshing simulation. And SBR, shooting and bouncing rays, provides the ability to model electrically large scattering interactions and their effects on installed antennas. Now our solvers, finite element and SBR, are able to operate within a hybrid fashion or a hybrid framework. So the finite element results are actually used to excite the SBR simulation. This is performed automatically by the solution process. And next, at the end, we obtain a complete installed performance solution. Next slide, please. So here's our simulated installed radiation pattern, and here we're showing the copolarization and the cross polarization in a pattern cut that's in the XZ plane. So that would be a slice that goes across the solar panels on the device. Next slide, please. It's also possible to visualize the copole and cross-pole results in a full 3D radiation pattern that's superimposed as installed on the CubeSat platform. Now, the complete EM simulation required about 40 minutes and about 24 gigabytes of RAM on a 32-core workstation. The problem size for this is about 50 by 35 by 25 wavelengths, or about 40,000 cubic wavelengths at 30 gigahertz. This is not a very large problem for the SBR Plus solver, but it would be quite large for a full finite element volume meshing simulation if we only used finite elements. And that's kind of an illustration why you need a couple of different techniques operating in a hybridized fashion to accomplish something like this in an efficient and a time-conserving manner. Next slide, please. Finally, it's useful to compare the isolated antenna radiation pattern. Of course, that's what we would normally measure during the antenna design and validation phase, and compare it to the installed performance where the coupling to the CubeSat platform is considered. Now, just to note the plots, in the blue curve, we're seeing the isolated antenna pattern cut here for one of the pattern cuts. This again is along that y-axis across the panels. The red curve shows us the installed antenna, so that includes the CubeSat body interaction effects. And you can see here the main beam looks pretty good. Not much effect here until you're down about 10 dB or so. There's a little bit of some structure due to diffraction and reflections on the kind of the right-hand side of that plot on the transition region, but you do see the side lobes rise a bit. Now, in some satellite applications, and this will vary from antenna type to antenna type, and from satellite body interaction mechanism to, it's different for different satellite bodies. In some satellite applications, this rise in side lobe levels actually could be quite important, particularly if we're trying to protect a secure channel. Now, this installed radiation pattern is what we would then move into the AGI mission simulation for the RF telemetry downlink system evaluation in the context of a complete satellite in its mission profile. And with that, I will turn it back to Jeff.
All right. Thank you very much, Sean, and thanks, Ming, for that great explanation at the detailed engineering design level. So what we're seeing here is an image that shows the results of bringing that same exact antenna pattern that Sean just talked about and putting that on our CubeSat model at the same location, same geometry that we can then use within our link budget calculations. So we just simply browse to that file that Sean provided us, and then we model the rest of our transmitter parameters such as frequency, power, and data rate. And then we modeled the ground station antenna, put some environmental models on there, and computed the dynamic RF link parameters. So very easy to set up, very quick to do, and I appreciate you guys sharing that great example of how we're now able to integrate mission analysis into the detailed engineering design process. So that was one of the use cases we wanted to look at in imaging pass. The next vignette is something a little bit more notional here. And what we're going to look at is combining STK and ANSYS to analyze the performance of one of these satellites to track a hypersonic vehicle from space. And this is a challenging topic for a variety of reasons. So we're going to use these same existing systems and some notional data to explain the overall process and how it works. So this is the first step here is to set up the overall mission geometry, and we're still going to use that same spacecraft simulation that we have used in the previous vignette that we again designed from that, got the overall orbit geometry from the satellite constellation design. And then what we did was we calculated when that satellite would fly over a hypersonic target, as illustrated in this case. You can see the X-43 hypersonic vehicle in the upper right, our CubeSat on the left, and we've done some basic geometry calculations such as the look angles, the azimuth elevation, and range to target. You can also see on the 2D graphics in the lower right as the satellite is passing over the hypersonic vehicle. So that's kind of first step, is setting up the overall geometry. The next is to actually create the trajectory of the hypersonic vehicle and digging into that. So in this case, we're just flying due north at a constant angle of attack. The Mach number and altitude vary throughout the flight in a phugoid motion as illustrated in this screenshot here. And we have a data display showing the time, altitude, angle of attack, and Mach number, which we've passed over to ANSYS for higher fidelity CFD analysis. So with that, I'll again turn things over to ANSYS, turn it over to Valerio.
Thanks so much, Jeff. And with that in mind, just basically as a difference from what we just saw in the satellites, we're coming down into the atmosphere. And as Jeff has introduced, we are looking at an example of a mock-up geometry of a NASA X-43. And what we are doing from the CFD analysis is a detailed analysis of the thermal signature that such a vehicle would generate when flying a Mach 9 at the specified altitude given by AGI. So to give you an example of what it will look like, the analysis inside ANSYS CFD Fluent, we've taken the geometry, we specify boundary conditions. And if you look over here, we are flying, as Jeff mentioned, a Mach 9, about 120,000 feet. We're specifying the correct angle of attack. And we're also including the effects of the engine or the scramjet mounted on the X-43 so that we can see the effects on the infrared signature coming out from the plume of the scramjet. We have created, if you're familiar with CFD, a compositional mesh, and we have put the vehicle inside what we would call the compositional domain, in this case, just surrounding the vehicle and a little bit downstream. And we have created a compositional mesh. In this case, we are using ANSYS polyhedral mesh elements, and we also have inflation layers. And just looking a little bit more at details of the mesh, since it's always a big topic for CFD, you can see at the level of detail that there's a very good quality mesh everywhere, also in the problematic areas like on the fins and the nose. And taking a different view, we are looking at the inlet of the scramjet and the exhaust side of the scramjet. So we set up ANSYS Fluent. We are running in steady state. We're making some assumptions, some simplification to the problem, such as we're using a DL gas for density. Therefore, we don't have any chemical reactions, but that would be very easy to include in terms of modeling. And the next thing, we let Fluent do what it does best, run its simulations. And these are some of the results. We're looking at a cross plane on the plane of symmetry of the vehicle for the Mach number, and we can see the plume coming out from the scramjet at the back, and we can see the shocks in the front. And this one is just a different view in which we are plotting a simulated Schlieren picture. So what I'm plotting over here is the density, the gradient of the density. So we can see the shock, and we are coloring the surface of the vehicle with the temperature. And this one is just a quick animation showing the streamlines coming out from the scramjet and going into the intake of the scramjet. It's just different views of what would be seen by an infrared sensor. This one is the temperature distribution on the surface of the vehicle. And if you look over here, a temperature in Kelvin is extremely hot, both because of the plume coming out from the outlet of the engine, but also from the friction and the compressibility effects of this vehicle flying in Mach 9. And I'll stop over here, and I'll just say that we use the CFD to successfully create an infrared signature of the vehicle, and we are passing the data to AGI.
All right, so thank you very much, Valerio. This is another great example of integrating that mission analysis at the into the engineering design process, in this case at the CFD level. And so now what we want to do is take that that temperature profile and run it through our EOIR simulation to see if we're able to detect and track that that vehicle. So we set up our scenario, created our hypersonic trajectory, run a CFD simulation, and now we're going to do the EOIR simulation. And in order to do this, again, we're using this notional example with this Corvus BC CubeSat. And so what we'd have to do first and foremost is get a much better payload. So what we'd have to do is swap out the sensor model first of all. There's a thermal, or excuse me, a broad-based multi-spectral sensor, and then we have to put a new high-resolution thermal sensor, and we'd probably also have to give it a deployable aperture to help increase the focal length to detect a target like this. So yeah, purely notional, but when you do this with some of the parameters, we started with the existing parameters from the Corvus BC platform and then played around with them inside of EOIR, made some assumptions for how well we could potentially improve the system in the future. And this is the values that we use: the field of view, the F number, the focal length, the GSD, and in this case, we're going to be looking, instead of at the visible, where we'll be looking at the medium wave infrared spectrum here. So this is the results of after we've modeled that, put it all inside the mission simulation, and what we see in the upper right now is a synthetic scene of what that EOIR sensor would actually be detecting, and we can see that tiny blur at the center of the image representing our hypersonic vehicle there. And just changing the view a little bit more, so instead of looking at the sensor output, if you change that to just look at the radiometric input into the sensor, we can actually, and zooming in a little bit more, you can actually resolve the shape of that image, and you can actually see the same temperature map that was used inside of, and that was exported from ANSYS into STK. We can run that through the EOIR simulation to see those results here as well. So certainly a lot of detail here, a lot more we could cover. There's not enough time to go into this today, but this is just one piece of the overall problem. But STK can take this type of modeling, integrate this into the entire engagement chain, including scripting behavior with STK's programming interface. In that case, STK allows you to evaluate individual pieces of the chain, such as the detection and tracking from individual sensors like the one we showed here. Look at tipping and queuing, network latency, command and control logic, and engagement performance such as probability of intercept given the location and number of interceptors, countermeasures, firing times, load factors, things like that. And that can all be tied together inside the STK analysis environment for a comprehensive kill chain assessment. We just don't have time to go in that here today, and we're running short on time already. If you are interested in more on this topic, please put in the chat questions. But now what we're going to do is we're going to switch gears a little bit, and now that we've done all these detailed engineering design simulations, we want to show how to then bring that back up to the descriptive models in SysML, like we discussed at previous webinars. And we're not going to go into detail. The last webinar went into a lot of detail on this, but I at least wanted to level set for the folks that didn't see that. In the last webinar, we showed a satellite constellation, integrated that with descriptive models, validated requirements for image resolution revisit times. And so today's webinar, we really want to focus on the ANSYS piece, so the ANSYS integration at the subsystem and component level. And so in this image, you see the high-level block definition diagram of our satellite constellation. And what we've done is we've extended this model for today to include each of the satellites and its subsystems. So in particular, we've added our EOIR sensor model, as well as our Ka-band antenna, which has both a gain pattern and temperature that we showed in ANSYS. So here in the upper right, you can kind of see a snapshot of the component for the antenna. There's a temperature requirement on that, and you can also see the antenna component listed in the lower right, which was used for the link performance. So the way we integrated that was, again, using those parametric diagrams, and then once we have the parametric diagrams, we can expose those value properties into ModelCenter, which can then run directly through Cameo to validate requirements or other SysML tools. So with that, I'm going to turn it over to Joshua to talk about how quickly we were able to add the ANSYS updates here to our overall workflow.
So thank you, Jeff. Great presentation from ANSYS and from AGI. So I just want to kind of close the loop, and as Jeff said, kind of focus in on the ANSYS integration piece. We've touched a lot on integrating STK, integrating with Cameo. And so as a recap, in webinar 2, we looked at the capabilities of ModelCenter, specifically integrate and explore, to bring in STK and a cost analysis, doing some design space exploration and looking at some trade-offs between access, duration, and total cost. In the third webinar, just our last webinar, we went in great depth on building up our SysML diagrams, building up those parametric diagrams, and exposing those and the ModelCenter workflows tied to them, all within MBSE Analyzer. Running from here, kicking off the workflow behind the scenes and validating requirements for that ground sample distance and time to revisit. So what we thought we would work on today is a little bit of that, but focusing on the integrating ANSYS piece to really close the loop. So as we said, we've already focused on STK, Excel, Magic Draw, Cameo products. So now we're going to focus on the ANSYS piece. First off, before I do that, I just want to kind of level set and talk about file I/O automation, so file input output. So this is a typical pattern of running software either in a manual sense or from a programmatic sense, where we would have some basic input file. We see here we have deflection.in, has some input values and variables here. With file I/O, we have an input file that is usually consumed by an executable. In this case, we have an example for deflection.exe. So the executable consumes the input file and then produces some output file with variables. Usually this is run in batch mode, as we see here, this quick little command line argument where we've specified the executable, given some arguments for the inputs and outputs. So the title of this slide is for automation prerequisites, because anytime we're working with a file I/O program, we need to identify these key prereqs before we can actually automate and integrate those into ModelCenter. So the prereqs being the input file and input variables, the executable and any arguments to run it, and the output file and any output variables. So in the same way, with file I/O, everyone knows that ANSYS has a spectacular GUI. A lot of people are used to running it from that standpoint. What we require, though, is the behind-the-scenes kind of file I/O execution of ANSYS. And so the way we do that is extending that file I/O pattern over to ANSYS is we require input file. So we see a quick screenshot here where ANSYS allows us to record a journal file. We can perform some activities, some clicks in the GUI, and the journal will record a script for us. This will become our input file. The executable being ANSYS, in this specific case, ANSYS Workbench. So we'll need to call the ANSYS executable. And then for our output file, also in the ANSYS Workbench GUI, looking at our parameters, we have the options to export our data out to a CSV. So this CSV will become our output file that ModelCenter will parse and give us the output results. And just as we said previously, we need to know how to run this from a batch mode. In this case, we have a simple command here of how to run ANSYS. We have the run workbench executable, a couple commands pointing to the project, and a couple arguments pointing to the journal file, which was that input file. So moving forward with that, we're going to show how we're going to integrate ANSYS into ModelCenter. And the first thing we're going to bring up is ModelCenter's Quick Wrap plugin. So Quick Wrap can handle any file I/O program. In this case, we're going to focus on ANSYS. And this is the GUI for Quick Wrap. It's going to be quite simple. I'll even show a demo of bringing in ANSYS, where we'll actually step through this little quick start ribbon here at the top to bring in all our prerequisites. So the input file and its input variables, the output file and its output variables, the executable and any arguments and the commands to run, and then we can even test run as if we were running from the command line. So without further ado, I'm going to hop into a very quick example. This will move fast-paced, but this is bringing up or automating the thermal analysis that Ming described earlier. So we're just going to focus on one of the use cases that the ANSYS engineers presented. Like I said, in this case, looking at the antenna temperature from the CubeSat. So to start off with, we'll go ahead and bring in the ANSYS plugin. Like I said, this is Quick Wrap. We'll start working down the quick start menu. We'll go into the input file specifying our journal file. And then we'll need to expose the input variable. So in this case, this is the emissivity. First off, we need to be able to parse this text file, which is kind of unevenly distributed. So what we'll need to do is grab this single variable here and expose that as a variable. So we have the emissivity wrapped. We see over in the top left, we've added that as a variable. And now we'll move into the output file. So we're going to grab that CSV, that ANSYS output. We're going to look at it just as a plain ASCII text file. And we're going to do the same thing we just did with the input file. And so we see here, this is an output of all the parameters from the ANSYS Workbench project for that antenna temperature. Here in this second value, we have the antenna temperature, or the max antenna temperature, I should say. And then we're also going to expose the variable to the left of it, which is going to be the overall spacecraft max temperature as well. So quick little appending of max to this, always good to keep the details straight. And then next we'll need to specify that command line argument that we showed earlier. So in this case, we see that run workbench, we see the pointing to the journal file and the project. Doing a quick test run, we see we've spit out some outputs down here in the bottom. Jumping over into ModelCenter, we can change up these emissivity values as needed, run, and fast forward through the calculation time and see that we actually get updated values for the antenna temperature and spacecraft temperature. So once we've done that, of course, we've already touched on how to integrate STK, how to bring in other models and so forth. So we're going to kind of skip to the end and kind of show the final picture here, bringing back those parametric diagrams. So we see here the parametric diagram. In this case, we have a constraint block here in the middle that's going to point to the integrated workflow that we've constructed, bringing in the value properties from the SysML model, running the calculation, and then pushing those values back to the output value properties. So in doing that, if we run this from MBSE Analyzer, we had some requirement on the downloaded imagery. And in this case, we've actually, we've run this beforehand, taken a screenshot of it, and presented. So this is bringing back that imagery that Jeff and Ming were talking about pointing back down and making sure that that requirement can be met. The second vignette or use case that Jeff was talking about was for the EOIR detection. So we can go ahead and tie that integrated workflow into the second parametric diagram here, doing the same procedures that we've shown before in the previous webinars. Fast forwarding to the very end, we can see we have a collection analysis on this one where we have a requirement on collected imagery and the image signal to noise ratio. In this case, we've run our workflow beforehand once again, and we get check marks that we've passed those two requirements. And just to bring that back to what we were referring to, this is the capture of that hypersonic vehicle, making sure that we can, in fact, get validation of our requirements for that use case. So bringing that all in, like I said, in closing the loop, we can integrate workflows, bringing in the STK mission model and the detailed analysis of ANSYS. We can import those into the Cameo SysML model, and we can run that from MBSE Analyzer, validating the requirements and executing that workflow behind the scenes and verifying that in all, we're all working from an authoritative source of truth, doing detailed design and moving from left to right, from conceptual down into detailed. Jeff, how are we looking on time? I'm going to just talk to this very quickly, as all my other appearances here with the AGI webinars. I've touched on an industry example with a quick webinar citation. In this case, Northrop Grumman did a phased array antenna trade study. I'm just going to flip through this very quickly. Of course, they integrated a multitude of different tools, including ANSYS HFSS. But I think one of the key points here that really fits into the AGI DME philosophy is looking at this top piece right here. We see that we can bring in all our systems models. We can start at a low fidelity, working in 1D or 0D calculations, kind of back of the envelope calculations with scripts or Excel. But we can slowly move at our pace into higher fidelity, which includes bringing in detailed analysis tools like ANSYS. So in this case, we're moving from left to right, and then we're bringing in, and as our design and our requirements mature, we can move from left to right with the conceptual to the preliminary to the detailed, and increasing the fidelity of our tools and swapping those into our workflow at any time. And just a quick little showcase of the results here of doing some trade-offs and some Pareto front optimizations between multiple objectives.
All right. Thank you very much, Joshua. Yeah, I'll go quickly through the summary and try and leave as much time as I can for questions. And then we're approaching the end of the hour here. All right, so just wanted to circle back to what we really presented since the start of this webinar series, which is what the vision is of digital mission engineering, which is really to connect all of the engineering and systems models to the mission model that is rooted in a multi-domain physics environment. And what we showed in this webinar series is having all of these pulled together as early as possible, having these commercial tools that are pre-integrated from day one, allows us to do high fidelity simulations. It allows us to identify critical issues or problems with the design early on that would impact our mission requirements and make changes at an early stage. And then we can also use those and explore different mission vignettes at various phases of the life cycle. We discussed the concept of the digital thread, which illustrates how each of these models are individual strands that are all tied together. So when you pull on individual parts of one model, it pulls through the rest of the models as well. We showed how using ModelCenter as that common framework to do that, linking all of the inputs and outputs from each of the tools so that as one changes from one tool, it feeds to the next one. And that's all integrated with the authoritative source of truth within the SysML descriptive model. And we talked about really just having all those tools so that you don't have to integrate scripts, as we showed in the broken lines diagram earlier, with all of the isolated tools, the time it takes to develop those custom tools at each phase of the life cycle, and then integrating them as you go. It makes it really difficult to identify those critical issues early on in the process, which can limit your overall delivered effectiveness. And how standardizing on these organization-wide allows you to transition from program to program, maintaining that knowledge and not having to rebuild custom tools each time, and really just alleviate significant challenges of maintaining custom tools and then transferring knowledge as individuals change programs or leave the organization. So a quick summary here of the different tools that we highlighted. We used STK for the mission model. We showed how it integrates with other tools through the program interface directly or through ModelCenter. We talked about ANSYS. We only covered these main three product lines, the electronics, mechanical, and fluids in this webinar, but talked about how you can integrate STK with those. And then with ModelCenter, we showed how to integrate, explore, and then use MBSC to link up with the SysML tools. So again, I wanted to thank all of our presenters today. I want to thank everyone for attending today's presentation. There's a bunch of next steps here. There's all of these webinar videos will be available by going to agio.com/DME. And if you want any more information, I know we covered a lot of ground today in a short amount of time. So either visit our websites or send us an email, as you see here. And also, I wanted to mention that we are planning a digital mission engineering roadshow where we're going to allow different presenters to present on these topics like these and then go into more detail on select topics. So we're planning to roll that out in the early to mid-November timeframe in the DC, Denver, and Los Angeles areas. So stay tuned on that. More information coming soon.
So you ready for the questions, Jeff?
Yeah.
Okay, I got a couple here that came in around the same time. I'm going to read them all at the same time because they sound pretty related. The question is about simulating plasma physics in terms of local and non-local thermodynamic equilibrium flow, solving work in plasma engineering like RF ion thrusters, and modeling the plasma pattern.
Valerio, can you take that one?
I'll take that one, and I think, Sean, if you want to pitch in as well from the HFSS side, but what I can tell you is we actually are presenting next week a poster presentation at the Hypersonics Technology and Systems Symposium or Conference down in Alexandria, Virginia, on communication blackout. I know that's not plasma, but that is a first step that we are doing towards the modeling of these ionic fields and the interaction with radio frequencies. And on the magnetohydrodynamics, on the plasma, pure plasma, we are working on that. We do not have a full-blown ready-to-use a solution just as yet. But we can model, we can compute the ion concentration and distribution around the vehicle.
Yeah, thanks. I'll just pick up from where Valerio left off. Once you have that ionic distribution, it is possible to compute a position-dependent sort of a material property or conductivity sort of characteristic for the ion sheath around the vehicle. And I'll be stealing our thunder a little bit, but we have a release of HFSS coming out here very soon that will have position-dependent material property capabilities, so that one could have a position-dependent complex permittivity, complex permeability, or conductivity values. And that can be, as I said, position-dependent within a volume. So we anticipate that we will have, on the electromagnetic side, the ability to then compute how electromagnetic energy is affected by that sheath.
Okay. Next question here is designing for the flat wavefront out the exit important? And that came in, I think, Sean, while you were presenting.
Well, I think what's important is whatever you need to do to the design in order to maintain a coherent beam. I think that the fact that they are fairly consistently flat as the wavefronts exit are sort of part of what's important to keeping a very focused shaped beam. Of course, we want to conserve power. The transmitter can use less power if we can concentrate more of the energy in a tighter beam. So we use, because of course we're limited by physics in terms of how large the aperture can be, unless we use a reflector or something else, a little bit larger. But that would be one of the characteristics that we'd want to see that lens does. It takes the wavefronts and bends them down flat once they exit that aperture, in order to again create that nice shaped beam and keep all the energy where we want it.
Great, thank you. All right, another question is, how do we integrate this ANSYS with STK to implement it in our simulation? I think that one might be a little bit too in depth to go through in this forum, but we could follow up with you on that question, because I think this was just an example of doing it, not the specifics of how to do it covered in this webinar. Similar question, or similar answer rather, not a similar question. Can you go into the C2 chain, as you mentioned in this webinar? Jeff, you were the one that mentioned that. And I think there is an example of a case study on that on our website, the Air Force A9, but for more info, we're going to follow up with you on that one, because that's not something that we can go into a whole lot of detail in this forum here. Can your software pass the target data around the satellite network to the same fidelity to used by other satellites?
Pass the target data. I'm guessing this was the target data from the EOIR sensor. Same level of fidelity by other satellites. I guess I probably need a little bit more clarification. I think one thing I'll mention is that once you have that data collected from your sensor, you can model the crosslinks from multiple satellites and then downlink it to the ground stations, and you can model that to a high level of fidelity. But I'm not sure I follow the rest of the question, so we'll follow up with that one.
That one sounded a little specific, so it'd be better to have a more detailed discussion afterwards, I think. Question, this one says it's for Phoenix. How do two companies collaborate on a project together?
I'm happy to answer this. I think everyone could probably chime in on this one. It takes a good amount of meeting and understanding and communication. Of course, I know that's probably a cliche answer, but I've gotten to work with Jeff now for a few weeks, and then also the ANSYS engineers as well. So making sure that things are defined up front, we all have a common vision, and then it's just a matter of getting the work done, so to speak.
Great. Thanks, Joshua. So another question about, we had covered a lot of topics today, and there's a question of, well, what are all the tools that you guys went over here? And I know the specifics about what you're trying to do, there's probably a follow-up question because there's various aspects of each one of the tools. But Jeff or anyone else, can you go through sort of the laundry list of everything that you showed today to show the workflow front to back on this?
Yeah, I guess I can take a stab at that. So the overall products that were used were ANSYS products, AGI products, specifically the STK product line, ModelCenter, as well as Cameo. Now, I don't know all the details in terms of specific packages within each of those product lines. I talked briefly on the ANSYS products that were used. On the AGI side, we used a variety of modules within STK. We used the Aviator to do the hypersonic vehicle. We used EOIR for the EOIR simulation. We used SAT Pro for the constellation design, and Analyzer for the trade studies and integration with ModelCenter. We used SOLIS for the spacecraft simulation and attitude control system. I'm probably forgetting a couple others, but those are at least some of the products that we used on the AGI side. You don't need to necessarily use that specific configuration to do this type of workflow within digital mission engineering. There's lots of different vignettes or use cases that can be applied, whether it's an air mission, a missile defense, space design. So that is probably more of a follow-up on and see what specific problem areas and application areas are you looking to address, and then we can provide a more specific recommendation of specific modules for your use case. I don't know if Phoenix or if ANSYS wants to add in on that.
I can do mine very quickly. The three products match the same three capabilities that Phoenix has. That's ModelCenter Integrate for integrating and automating, ModelCenter Explore for exploring or optimizing your design space, and the third is ModelCenter MBSE for the bridging between the descriptive and the domain engineering analyses.
ANSYS Electromagnetics, it's the HFSS, High Frequency Structure Simulator, and the HFSS SBR Plus simulation option for it. Over on the fluid sides, it's Fluent for the hypersonics modeling, and on the thermal modeling, it's the ANSYS Mechanical Suite.
Great. All right, well, that's all the time we have today for these questions. If we didn't get to your question, we will follow up with you individually with the appropriate company answering your questions, or companies. Thanks again to all of our presenters. If you are looking for the slides and this recording later, it is going to be available at agi.com/DME. That DME stands for Digital Mission Engineering. So if you go to that website, it's an easy way to stay in the loop about other upcoming digital mission engineering events that we will be having in the future. And again, thanks again to all of our presenters. Thanks, Jeff.
Thank you, Joshua. Thanks, guys. Bye.